Okay, this is just a short video on the dot product. And I'm mostly not going to go into proofs, but we are going to handle a couple ideas. First thing is the way the dot product works. If two vectors are perpendicular, then their dot product is 0. If two vectors are parallel, then their magnitudes are multiplied. That's really the only two things we need to know. We'll actually be able to work everything out based on just those two facts alone. So let's say we have two vectors, vector A and vector B. Vector A is AX in the I hat plus AY in the J hat plus AZ in the K hat, and B is much the same, BX in the I hat, BY in the J hat, BZ in the K hat. Well, if we think about these rules, I hat dot I hat is equal to 1. J hat dot J hat is equal to 1. K hat dot K hat is equal to 1. How do we know that? The second rule. These are unit vectors. They have a length of 1 and they point in particular directions. I hat with I hat, they're the same way. J hat with J hat, they're the same way. K hat with K hat, they're the same way. So we get a magnitude of 1 because 1 times 1 is 1. If we take I hat dot J hat, though, we get 0. Why? Because they're at right angles to each other, so they will multiply together to nothing. I dot K, also nothing. If we keep going with this, J dot I is nothing. J hat dot K hat is nothing. K hat dot I hat is nothing, and K hat dot J hat is nothing. So there are 6 cases that lead to 0 and 3 cases that do not. If we imagine taking these vectors and trying to multiply them together, if we're trying to multiply the I hat component by the J hat component, we're going to get 0. So any cross components will die out. I dot J, I dot K. So when we try and do, vector A dot vector B, let me take this and move it down actually where I have lots more space. You can kind of think of that as being AX BX I hat dot I hat plus AX BY I hat dot J hat, and you can already see how this pattern is going to go. AX BZ I hat dot K hat. And you can keep going through and going through and going through. There will be 6 more terms. AY BX, AY BY, AZ BZ, J hat dot I hat, J hat dot J hat, and J hat dot K hat. Final set, AZ BX, K hat dot I hat, AZ BY, K hat dot J hat, AZ BZ, and then we get K hat dot K hat. All right, so out of these 9 terms, the first one, I hat dot I hat, is 1, and it survives. So we get AX BX survives. AX BY is 0, AX BZ is 0 because I dot J is 0 and I dot K is 0. J dot I is 0, but AY BY survives because J dot J is 1. So So A, Y, B, Y. And then the third row, 0, 0, and we get the A, Z, B, Z. So I said I wouldn't really do a proof, but this kind of sort of was. I just didn't prove why I hat dot I hat is 1 and why j hat dot j hat is 1 and why I hat dot k hat is not. But this gives us the result. So this is the main thing we are after. We're 5 minutes in, and I'm going to show one more thing because there is another way of writing the result. A dot b is equal to the magnitude of the a vector times the magnitude of the b vector times cosine of the angle in between. And we can actually think about that in the following way. Imagine you have your vector A pointed in a particular direction, and then your vector B points at some angle to that. If you only have two vectors, it's guaranteed that they're either going to be parallel, anti-parallel, perpendicular, or you'll be able to make a plane that contains both lines and the angle in between. So if we take a look at this, imagine taking vector b. We can split it into components. We've done this many times in the past. We can find the bx component, let's call it, and the by component, where the bx component is aligned along A, and the by is perpendicular to A. Well, we know perpendicular components. If we try and take the perpendicular component vector of b and multiply it with A using the dot product, that's going to give 0 by our first rule above. But the bx and the a, those will multiply together. Now let's think about how those are made. Bx would be equal to the magnitude of b times the cosine of the angle, and by would be equal to the magnitude of b sine of the angle. Let me clean up that b. So you can see if we take the bx component and we dot product that with the a, we're going to get the magnitude of each, magnitude of A, magnitude of B, and the cosine of the angle. Okay, so now we have both ways of calculating the dot product. This will be useful for calculating the work because work is defined as force dot product with the displacement vector, or being really proper, the integral of the force dot product with the dr vector, where dr is an infinitesimal displacement. All right, so we're going to call it there. Nice 7-8 minute video. More than enough information for you to handle dot products. You can look up some examples later, and hopefully we'll have one of those in class when we get there. All right. Oops.